Welcome back to the deep dive. Today, our mission is to tackle two really powerful analytical chemistry techniques.
And it can be a bit intimidating, right?
For sure. We're talking about atomic absorption spectroscopy and nuclear magnetic resonance. Our goal is to give you a full, concise, and, well, a genuinely useful deep dive. We're really looking at the difference between figuring out what elements are in your sample versus figuring out the exact molecular architecture of that same sample.
Two very different questions.
To set the table, we are looking at two fundamental branches of spectroscopy. First, you've got atomic spectroscopy.
Yeah.
And that's all about how light, or electromagnetic radiation, interacts with individual isolated atoms.
And then the other side of the coin.
Molecular spectroscopy,
Yeah.
where the radiation is interacting with the whole molecule, which tells you about bonding and structure.
And that contrast, I mean, that's the key to understanding today's deep dive. We're drilling down on AAS, which is your element detection tool, and NMR, your structural mapping tool. So if you're, preparing for a meeting, or you're just curious how labs confirm contaminants or identify new drugs, these two techniques, they underpin huge swaths of modern chemistry and biology.
So let's start with AA, atomic absorption spectroscopy, the element hunter.
Good name for it.
What I find incredible about it, really, is its simplicity when it comes to the sample. You don't need to isolate your target element, say, lead from everything else in there before you start.
That is its core utility.
Yeah.
Specificity and sensitivity. It's designed to hunt one element at a time, but very efficiently.
And we can detect a lot of them this way.
Oh, yeah. We're talking about the ability to detect roughly 70 different elements, and it's fast. That speed is, well, it's critical when you need quick confirmation of trace metals, maybe in an environmental or a food safety context.
So the output is fast, but the preparation to actually make the element detectable, that sounds deceptively complex. You can't just shine a light on a solid chunk of metal, can you?
Absolutely not. No. The real operational challenge in AAS is getting that metallic sample into the very specific light-absorbing state that's required.
And that process, from a metallic salt, an MX in solution, to a ready-to-absorb atom, it has a few steps.
It has 6 transformative stages, actually.
Let's walk through those 6 stages, because I think this reveals why the instrumentation is so specialized.
So you start with your metallic salt, which you've typically put into a solution. That solution is then sprayed into a fine mist, or droplets. We call that nebulization.
Like an aerosol can.
Exactly like that. Next, that mist evaporates, leaving a solid residue. Then that solid is vaporized, turning it into a gas.
And this next step is the key one.
This leads to the critical step, dissociation. The molecule literally breaks apart into its constituent atoms. Only after all that physical effort do you have the isolated ground state metal atom, the M gas.
And it's this ground state M gas that is finally ready to absorb light. So the AAS instrument isn't measuring light being emitted from the sample, it's measuring what's being absorbed.
Exactly. The final 7th step is that absorption of a specific wavelength, which kicks the atom into an excited state, M star. And the amount of light it absorbs is proportional to the concentration of the element.
And this is where the cost and complexity of the hardware really jumps in, because to make sure only your target atom absorbs light, you can't just use a normal light bulb.
No, you need a highly specialized source, the hollow cathode lamp or HCl.
Yes, and this is AAS's greatest constraint, isn't it? You need a different HCl for almost every single element you want to analyze.
That's the one. If you switch from testing for copper to testing for zinc, you have to physically get in there and swap out the lamp.
So why the constant swapping? Why is it so specific?
It's because the lamp itself generates the exact specific wavelengths that only that element absorbs. So the HCl is basically a glass tube filled with an inert gas like argon.
Okay.
And inside you have 2 electrodes. Crucially, the cathode, the negative one, is made of the very metal you want to analyze.
So if I'm testing for gold, the cathode is literally made of gold.
That's right.
How does a lamp use a chunk of gold to generate light?
So you apply a strong electrical potential across the electrodes. This ionizes the inert gas, and those positive gas ions, they accelerate toward the negative cathode and just smash into it.
Violently.
Violently, yes. This process is called sputtering. Metal atoms are physically ejected from the cathode surface, and those ejected atoms then become excited by more collisions, and when they relax, they emit the ultra-specific radiation signature of that element. And that's the light we shine through our sample.
It's a beautifully tailored light source. Which I guess helps explain why the instruments themselves are so costly and why analysts need specialized training. They're managing a very complex system.
A system of tailored light sources and, as you'll see, highly controlled temperatures. Speaking of which, let's talk about the atomizer itself.
Okay.
So after the nebulizer turns the sample into mist, the atomizer's job is to apply heat to get those dissociation and vaporization steps done.
When we think atomizing, we usually think of just immense blazing heat. But the critique we saw suggests the temperature of the flame is actually kept, well, pretty low. That sounds like a paradox.
It is, but that's the critical operational balance. You need enough heat to break the molecule apart, that's the dissociation, but if the flame gets too hot, you cause ionization.
Ah, so the atom loses an electron.
Precisely. And an ionized atom is no longer in the ground state. It cannot absorb the light from the HCl, and your analysis completely fails. So the atomizer is constantly balancing vaporization against preventing ionization.
It's a tightrope walk. You have to thread the needle perfectly. And the equipment to do this, the burners, they also involve a trade-off. There are two main types, right? The total consumption burner.
And the laminar flow or premix burner, yes.
So the total consumption burner mixes everything right at the flame. It's safer, I gather, no explosion risk.
Safer, yes, but it gives you lower efficiency and it can be noisy. The laminar flow burner, on the other hand, it mixes everything in a chamber before it gets to the flame.
Which gives you much better atomization efficiency and better reproducibility. So your results are more consistent.
Exactly. But you carry that inherent risk of having a volatile mixture in a chamber, which requires careful control to, mitigate the possibility of an explosion.
And for fuel.
The most common is acetylene mixed with air. That runs around 2100 to 2400 degrees Celsius. But the analyst has to pick the fuel based entirely on how easily the atom of interest vaporizes.
Okay, so with all this complexity, high heat, precise light, dissociation, it's no surprise that TAS can suffer from several types of errors or interference. Let's touch on the two biggest ones.
The first major one is chemical interference. This happens when your element forms a stable compound that just refuses to fully break apart in the flame.
For instance,
if aluminum and magnesium oxide form, they stay stuck together. This drastically reduces the number of free atoms available to absorb light, and you get an inaccurately low reading.
And the fix isn't just turn up the heat, because that leads to our second problem.
Precisely. The second is ionization interference, which we just talked about. The flame is too hot, it ionizes the atoms.
So how do you fix that?
The classic solution is to basically overwhelm the system with electrons. You add an easily ionizable element, like potassium or cesium, to your sample. They ionize really easily, creating a high concentration of free electrons in the flame.
And those extra electrons suppress the ionization of your actual target.
It forces your target element back into the desired ground state. It's a preemptive strike against ionization.
And once you've done all that, you measure your standards, you plot your curve, and you can reliably figure out the concentration of that unknown metal.
That's the process.
Okay, let's transition completely. We've established AAS is all about extreme control of light and heat to count elements. Now we move to NMR, nuclear magnetic resonance,
A completely different world.
which ignores light and heat altogether and focuses on a radically different property, nuclear spin and magnetism. We are moving from identifying what to mapping how atoms are connected.
And what's so fascinating here is that we shift our focus from, manipulating the sample to the inherent properties of the nucleus itself.
The nucleus has to have a certain property, though.
Yes. For NMR to work, the nucleus has to have a nuclear spin, represented by I, that is not zero. That's why we primarily study hydrogen-1 and carbon-13. Both have a spin of 1/2.
And that's why we can't study the most common form of carbon.
Exactly. The highly abundant carbon-12 cannot be analyzed because its spin is 0.
So we take a sample that contains these nuclei with spin, we put it into this giant machine. What happens then?
The NMR instrument applies an extraordinarily powerful external magnetic field. This field causes those nuclei with spin to align either with the field or against it.
Okay.
For a spin of 1/2, this creates two distinct energy levels. We then hit the sample with a pulse of radio frequency energy, which is just enough energy to flip the nuclei from the low energy state to the high one. That's the resonance we detect.
And the quality of the map, the structural detail you get out, is directly tied to the power of that magnet.
Absolutely. The stronger the magnetic field, the higher the resulting resonance frequency, which we measure in megahertz. A stronger magnet is a game changer for two reasons. One, vastly increased sensitivity, so smaller samples, and two, far less overlap in the spectrum. making the structure much easier to solve.
Hydrogen H1 is still the star of the show, isn't it?
Oh, for sure. It was the first nucleus used, and since it's almost 100% abundant in organic compounds and has a strong signal, it gives us an immediate window into the molecular structure.
When we look at that resulting H1 spectrum, there are three critical insights it provides. First is the number of peaks.
Right, the number of peaks tells you about equivalence in the molecule. If two protons are chemically identical, they give one combined signal.
Okay, so that tells us how many distinct types of protons we have. But what about the position of those peaks along the x-axis?
That position is the chemical shift. This tells us about the magnetic environment around the nucleus.
It's neighborhoods, so to speak.
Its neighborhood, exactly. Protons near electronegative atoms like an oxygen or a fluorine, or near double bonds, are shielded less by surrounding electrons. This causes their signals to appear further downfield on the spectrum.
So if I see a signal way downfield, I know that proton is probably sitting right next to an oxygen atom. That's a huge clue about the functional group.
Precisely. And the third piece of information is the most powerful for connectivity. Spin-spin splitting. This is where the signal of a nucleus is split by the presence of neighboring magnetic nuclei.
And for hydrogen, we follow a simple rule.
For H1, we follow the n+1 rule, where n is the number of chemically equivalent neighboring protons. If you have two neighbors, your signal splits into 3 lines, a triplet.
Now, this is a point that often confuses people, the difference between the chemical shift, which is in parts per million, or ppm,
And the magnitude of that splitting.
which is the J constant.
That distinction is crucial. The chemical shift is relative to the powerful magnetic field. So if you run the same sample on a stronger magnet, the ppm values stay the same, but the distance in hertz between those signals actually increases.
But the J constant doesn't change.
The J constant is a physical property of the molecule. It represents the actual magnetic coupling between neighbors. It's measured in hertz, not ppm, and it is completely independent of the magnet strength. It's the constant signature of that specific molecular bond.
So the J constant tells you about the molecule, while the chemical shift tells you about the environment relative to the instrument. That's a great way to put it.
And we need a reference point for all this, which is provided by TMS, tetramethylsilane. All of its 12 protons are identical, so it gives one sharp peak that we just defined as 0 ppm.
And a quick practical note, analysts use deuterated solvents, right?
Yes, meaning the hydrogen is replaced with deuterium. It has a different magnetic frequency, so the solvent doesn't contribute a giant, messy peak that obscures your actual sample.
A necessary step to clean up the data. And speaking of data, modern speed comes from a technique called pulsed FTNMR.
Right, Fourier transform. This replaced the older, slower method that had to slowly scan through all the frequencies.
How does pulsing speed up the analysis so much?
Well, instead of a slow scan, FTNMR hits the sample with a short pulse milliseconds long that contains a broad range of frequencies. Think of it like hitting a large ball with a hammer.
Ah.
That single hit excites all the relevant nuclei at the same time. They all start ringing and then gradually decaying back to equilibrium.
And that collective ringing signal is what the machine measures first.
Yes, that's the free induction decay, or FID. It's a complex wave pattern of signal intensity versus time. The computer then applies a mathematical process, the Fourier transform, to deconvolute that time signal into the clean frequency spectrum, the plot of intensity versus ppm that we actually read.
Why does that decay, the relaxation, take so long? We noted it can take several seconds, which seems incredibly slow compared to light absorption in AAS.
It's because energy loss in NMR is a much gentler process. We track 2 main relaxation types. First is spin lattice relaxation, where the nucleus gives its excess energy away as heat or motion to the surroundings, the lattice.
Okay.
Then you have spin-spin relaxation, which is basically the nuclei just getting out of sync with each other, causing the net magnetic moment to collapse. Both processes contribute to that long FID time.
So when the molecules get really complex, a simple one-dimensional spectrum, like the H1 we just discussed, often doesn't cut it. The peaks just overlap.
It becomes a puzzle that's too hard to solve. And this is where advanced 2D techniques become essential. This is where NMR truly shines.
Like CoOY.
Yes, QOAY, or correlation spectroscopy. It's a 2D technique that helps simplify complicated splitting patterns by showing you which nuclei are coupled to each other.
So instead of trying to follow tiny splitting lines in a dense 1D spectrum, you're looking for a clear marker on a 2D map.
Exactly. You look for the telltale off-diagonal spots on the plot. A spot there definitively confirms an interaction coupling between 2 non-identical protons. It lets you walk down the carbon chain and confirm the neighbors.
And for analyzing the carbon backbone specifically, what are the key tools there?
We have DP, which is a 1D carbon-13 method. DP is designed to identify how many protons are attached to each carbon atom. Is it 3, 2, 1, or none? DPT answers that.
And for the ultimate connectivity map?
You use AT-core. It's a 2D technique that correlates the hydrogen-1 signals with the carbon-13 atoms they are directly bonded to. AT-core is indispensable because it directly maps the bonding structure.
So it sounds like while ATI requires you to heat, dissociate, and correct for errors to find a single element, NMR uses these increasingly sophisticated magnetic measurements to build a complete 3D puzzle of a complex molecule.
That's the perfect distinction. ATAS offers high-sensitivity elemental confirmation by forcing an atom into a specific state, which requires constant management of flame temperatures and very specific chemical interference fixes.
Whereas NMR provides deep insight into molecular structure and bonding. It relies on a high-power magnetic field to separate energy states, and the analysis all depends on understanding where the nucleus shifts in ppm and that precise, constant magnitude of the spin coupling, the Jake and Constantin Hurt.
Yep, that's the summary.
So we noted earlier that AAS requires a specialized lamp for every single element you want to test, made from the actual element itself. But NMR relies only on a fundamental magnetic property, nuclear spin.
Right.
Given that we know any nucleus with a spin of 0 can't be studied, like carbon-12, what might be the theoretical limit on the number of elements or isotopes you could potentially study using NMR, it's not just H1 and C13.
No, not at all.
Think about all the possible isotopes on the periodic table that meet that non-zero spin requirement. How many unique magnetic nuclei are left to map the world? It's a chemical frontier that builds directly on the principles we just unpacked. Something to ponder until our next deep dive.